So here's a visual of what's happening with eddy current testing when we do that. So here is that AC input on a coil right here, and that's producing that magnetic field, that coil's magnetic field, and it's going to interact with that conductive part, and then you can see the eddy currents forming in the conductive part. Okay, so that's where the term eddy current comes from. This is the coil, kind of the induction side of it, inducing currents in the part. Okay. And then those eddy currents now will create or induce their own magnetic fields 90 degrees to their orientation, right? Each is 90. So now you have new magnetic fields. So we went from, those eddy currents formed, and then those eddy currents are creating their own little magnetic fields right there. And they're traveling in the opposite direction of the original magnetic field at 90 degrees to the current flow. And those are then, that magnetic field is going to basically push back against the coil's original magnetic field. And so we're looking for those changes, and any kind of interruption to this surface, this part, is going to change how these magnetic fields from the eddy currents affect the coil magnetic field. And that's what our tester is looking for. So it changes, it creates an impedance shift in that coil. How easy is it for the tester to push current through the coil? Right? Impedance is, it's kind of the inductive version of resistance, right? It impedes the flow of current through that coil. And it's those magnetic fields pushing back, creating kind of a reverse current that does that. And it's a combination of, there is going to be a certain amount of resistance in the coil, right? Any length of wire has a certain amount of just straight up resistance. If you were to take that coiled inductor and you were to straighten it out, right? It would be a piece of wire, it would have a certain amount of just straight up resistance in there. Because no material is a perfect conductor, especially at room temperatures. They have some near perfect conductors that like near absolute zero, but we're not dealing in that realm here. That's theoretical physics. So we take that wire, that's the resistance element right here. The things that are taking place with all these magnetic fields, where the magnetic field formed by the eddy currents is pushing back on the coil's magnetic field, that is the inductive reactance right here that's on the y-axis. And again, it's 90 degrees, that pushback it's not pushing back right away, it's delayed 90 degrees in phase, or 90 degrees to the phase. And so that's going to cause a change in the total impedance. And so the point where, that on our most eddy current testers that are just looking at this impedance, it's going to move that indication around on that display. And so that's what we're looking for. So if we have a probe on a piece of material and it's homogeneous, there's no cracks, there's no changes in it, if we move that probe around, this point shouldn't move anywhere, it won't shift. But as we're moving our probe around, if we go across something like a crack or corrosion, or even the thickness of the paint changes, it's going to cause a slight shift or a slight change in the inductive reactance, and it's going to cause an overall shift in the impedance. And we'll see that in the form of the indication moves on the display. And the magnitude of that shift, the magnitude of that impedance shift, gives us some idea of the relative size of the change. Now, the only way we can know that, though, is we have to have a standard to compare it against. So we use a standard, for instance, for cracks that have known crack sizes in it, that have been made in a machine shed. It's machined to have cracks of certain sizes, or simulated cracks of certain sizes. So some of the standards we have like an 8,000 crack, an 8,000 steep crack, and a 15,000 steep crack, and a 21,000 steep crack. And so as you go across each of those, you get a different shift in your impedance. The material affects this, the coating or the thickness of the coatings on it, the thickness of case hardening or heat treating or nitriding can affect it. The geometry of the part can affect it, as we'll see as we get through. So, there can be non-relevant indications that form due to the geometry of the part as well, or the features of the part. A rough surface causes our probe to, changes. There's little gaps below the probe face that can change this as well. So a few things we need to know about eddy current testing, or eddy currents, and kind of some vocab here. The current density, this is essentially how strong, the amount of eddy currents in a given area. How strong of currents are you able to induce in a material? Different materials are going to and it's primarily based on how conductive they are. It's going to be easier or harder to form eddy currents in them. Or you're going to form more eddy currents or less eddy currents in a given material at a given, power and other settings on our probe. So the current density, ultimately, the reason it's important is it's going to affect the accuracy of our test. Okay? Sometimes it's good to have high current density, sometimes it's bad. So current concentrates, it's primarily going to be at the surface of the material, closest to that magnetic field, right? As that magnetic field coming off the part, or off the probe, goes into the part, it's going to get weaker the further it moves away. So that makes sense that the strongest currents are also going to form closest to the face of the probe, or closest to the surface of the part. So the area closest to the coil. As you move away, there's an exponential decrease in the current density as you move away from the face of the probe, vertically, horizontally, at an angle. And so this allows us to get what we call our depth of penetration. Based on what kind of current density we have, we can figure out how deep, with a given probe, with a given set of settings, how deep of a discontinuity we can find. If we're looking for surface cracks, we don't need to have a lot of depth of penetration, right? We want to look at the surface. If we're looking for corrosion on the backside of a piece of metal, we have to set up our probe and set up our tester settings in order to get a better depth of penetration to see further into the part. But that also then causes what's called a skin effect, because those eddy currents form closest to that surface. They also can kind of mask things that are deeper, or they can mask discontinuities that are right at the surface. So if you're trying to find corrosion on the backside, your probe you may not be able to see, and I say see as you may not be able to see the effect of something that's near the surface, because the eddy currents are so strong that it's overwhelming the probe's ability to see that area. So you have to kind of balance that depth of penetration based on the depth of the expected flaw you're looking for. So the depth or the density eddy currents are proportional to the depth of penetration of the magnetic field. And we use something called standard depth of penetration to determine where are we able to effectively find information on a part. Find a flaw, find corrosion, determine case hardened thickness. So the standard depth of penetration is equal to roughly 37% of the density at the surface. Right? So the denser they are at the surface, the further the depth of penetration. It's the point where current density drops to 37% of what you would measure at the very surface. That's the max that you're able to effectively find an area of interest, a flaw, or some kind of indication, relevant or non-relevant, with a given probe and current setup. Below the standard depth of penetration, the signal is considered to be too weak to effectively test that area. Okay? So too close to the surface, however, it's very strong, and we're having a greater depth of penetration. It may overwhelm any ability to pick up or sense something near the surface. So if we look at kind of some diagrams that look something like this, this one's kind of given like a like ripples in a pond, like a contour map where you got the contour lines to represent strength of the field and the penetration. So if you have a very strong eddy current strength at the surface, In this case, you say that's 100%. Remember, this is it's not a linear decay, but rather it's exponential. And so where that eddy current strength falls to 37% of what it was at the surface, that's considered the effective, the standard depth of penetration where we could find something. So even though, in this case, the field and the currents are forming all the way down to this point at the bottom, we can only effectively, with this probe and these settings, whatever it's set to, we can only effectively find a flaw to this point right here. So you can see why this method is primarily for surface flaws versus subsurface. But with thin materials like sheet metal, you can use it to see backside corrosion and things like that. Another example with a heat map. So this is taken with a magnetometer heat map. You can see the probe coil here, and it shows where the where the magnetic fields in this case are the strongest, which also means where the eddy currents forming are going to be the strongest. So with a circular coil like this, it actually is kind of a donut shape. And this is a fairly, it's big enough you can see that separation. So there is a slight dead spot kind of in the center, but again, it's donut shape. As you're moving that around, you're not going to be able to get to that center dead spot without going through one of those live areas, that make up that donut. So here, if this is, density, more than likely, our depth of penetration is somewhere around the bottom of the yellow area, maybe right on the edge of the red. Again, you would have to actually take a empirical measurement of it to find that depth directly. But we can calculate that, and it can be affected by, for you, I'm primarily looking at what affects this. Okay, we don't have you, I don't have you calculate this necessarily exactly. It's a depth of penetration is approximated by this. There's more that goes into it. But for our purposes, if you need to do these calculations, these are the things we need to worry about. So depth of penetration is the square root of the resistivity, material's conductivity or resistivity, the material, how resistive is a material. And this kind of thing you would look up in a table. Materials are published, standard materials, they'll tell you how resistive is it. For a given distance or a given, area, how resistive is it, right? Something like copper or gold is less resistive, than something like steel, right? Copper is a really good conductor. Steel's a decent conductor, but not as good as copper, right? Something like the plastic that these tables are made of has a very, very high resistivity. Yes. Yeah, it's the square root of this entire equation. So it's the square root of this entire thing. So it's the resistivity divided by the frequency, which is the coil operating frequency. We can set that with our eddy current tester, times what's called the permeability. So we saw permeability in magnetic particle testing. That has to deal with the material's magnetic permeability, right? What's a high permeability material? What's something that's easy to magnetize? Iron, right? What's a low permeability material? What's something that's hard to magnetize? What's that? Brass, copper, any of those non-ferromagnetic materials. Aluminum, right? So our depth of penetration, right? We can't, well, on a given material, what I'm getting at is we can't control the resistivity, we can't control the permeability, right? Those are set by a given material. What we control is the frequency of our probe. And there's some other things. We can control how much power we're putting through the probe and other stuff. That deals more with like sensitivity at a given level. But, if we want to look for cracks near the surface, would we use a high or a low frequency? Higher or lower? So remember, this is below the denominator. This is in the denominator. It's below the line. A high frequency, right, is going to cause this to be a smaller number, right? This is fixed. Let's just say for our purposes, for a given material, these two are fixed, right? So the higher the frequency, The smaller the number, the lower the depth of penetration. So for finding things like surface cracks and that kind of thing, we're going to use high frequencies. 500 megahertz, 400 megahertz, something in that range. Several hundred megahertz range. Okay. If we want to find corrosion, which is typically we need a high depth of penetration. Consequently, then we need to use what kind of a frequency? Lower frequency, 1,000 hertz, 10,000 hertz, right? Instead of several hundred megahertz. Okay, so we have a pretty broad range of frequency adjustments we can make with our tester in order to control this depth of penetration. But just know when you go to a low frequency with a high depth of penetration, it also means it's going to form very strong eddy currents and magnetic fields at the surface. You're going to get that skin effect, and that's why you wouldn't be able to pick up both the corrosion on the backside and the cracks on the front side. It would be obscured by that. It's kind of like when you did dye penetrant. If you leave too much dye on the surface, you can't see the dye that comes up out of the crack, right? There are testers, in fact, ours don't. There are testers you can get that actually have special pros where they, not only do they, is the current swapping back and forth, but they can actually like change the frequency over and over. So if you're looking for both surface and corrosion, surface cracks and corrosion, you can have a dual frequency probe. So as you're running it across the part, it's swapping between two different frequencies and swapping current directions in order to basically check high, low, high, low, high, low, surface deep, surface deep, surface deep, surface deep. It's kind of going back and forth to try to find both. So here's what that looks like. So on the left with our high frequency, same material, same coil, high frequency, less penetration, but it's more sensitive. We can find smaller flaws like surface cracks we can't see. Lower frequency, we get that depth of penetration, but it's less sensitive. We can't find the smaller cracks, but typically internal corrosion, if we were able to take it apart, if we were to undo, drill out all the rivets and take the lap splice apart, we're probably going to see that corrosion. We're just trying to use this so we can test it in place without having to disassemble, peel the skin off our fuselage in order to look for corrosion everywhere that the skin laps together or everywhere that the skin is riveted to a frame or stringer on the inside. Right? We want to be able to check for corrosion pockets between those riveted structures without taking the whole fuselage apart. So, so they're bigger. You would be able to see them if you took it apart, but we don't want to have to take it apart. Here's an example of that table that gives you resistivity or conductivity. Conductivity, resistivity are inverse of each other. So here's a few different materials. So you can see this is percent IACS, which is basically the higher the percentage, the more conductive a material is. Okay. So, and it's based on copper as a standard. So if you say a copper is 100% conductive, is the most conductive material, right? Aluminum, 61% of that, right? Something down here like high alloy steel is only 2.9% of that. This is basically a 100% scale from not conductive, which is a resistor, all the way up to fully conductive. And then over here, you can see the resistivity is kind of opposite, right? So copper has very low resistivity, 1.72 micro ohms per centimeter squared. Whereas something like, our steel, certain high alloy steels aren't as conductive, 59 micro ohms per centimeter squared. So these are all still conductive materials in a way, right? But this is where we get these kind of tables are where we're going to get those, those kind of relativities. But again, aviation, like you have the plane sitting in front of you, it's going to be made of some kind of an aluminum alloy, probably. If you're testing for cracks and riveted skin. Obviously not if you're working on composite, but different animal, different test methods. So, that is, it's said, it just shows kind of what different materials are. Here's the permeability. So permeability is often compared to air. Air is considered to be approximately 1. Okay. Okay. So you can magnetize air in the presence of a strong enough magnetic field. This is getting into like plasma science and that kind of thing, right? Charged air, charged particles in the air. So if air is a 1, you can see here iron, which we know is highly permeable, very easy to magnetize, is 180,000 times easier than air to magnetize. Right? And you can see it falls off, however, very, very quickly. That's that difference between, why is iron ferromagnetic and other materials are not? You can see that giant difference that occurs right there. Going from the ferromagnetic material to everything else we consider ferromagnetic. Aluminum is not much different from air, right? You take that, you put an electromagnet near it, it gets magnetic fields formed, but as soon as you pull that away, it doesn't retain any magnetism, right? But the steel, permeability and retentivity are also linked, right? So this kind of gives you that. So again, if we're working with an aluminum airplane, we're not going to be able to change the permeability. We're just kind of stuck with it. So it goes back to that equation. The only thing we can really control is frequency. And then, again, we can also control how much power we're putting through the coil and stuff like that. Putting more power in it doesn't necessarily increase permeability or increase depth of penetration, because as it attempts to basically force that magnetic field further, you also get a stronger skin of magnetism forming, which prevents it from going deeper. So it kind of fights itself. You can increase or decrease the power to change things like sensitivity and how much resolution you get on your display, but it's not going to change your depth of penetration. Okay. So here are some of those inspection frequencies I was talking about. You can see that range is fairly large, right? 50 hertz at the low end to 4 megahertz at the high end. So frequency for thin aluminum parts, usually several hundred kilohertz, again, for finding those surface cracks. 400 kilohertz, 300 kilohertz, something like that, 250 kilohertz. Trying to find corrosion on the backside, 60 hertz, 100 hertz, 80 hertz. And we can use that range. And then in some cases, you go 4 megahertz, depending on the part, 4,000 kilohertz. Sometimes you use those higher frequencies for things like titanium or some of the other exotic materials, where you're trying to find very, very titanium. You need to, when you're doing eddy current testing, you are looking for extremely, extremely small flaws. Because titanium, you're familiar with the titanium grain structure? Did they talk about that materials? Why does titanium crack when you try to bend it? It has a crystalline structure that makes it particularly brittle. No? Okay. You know that titanium's brittle. It's strong, but it's brittle. So a very small crack beginning to form in it is a much bigger problem than a crack of the same size in aluminum, or even more so than a crack of the same size in steel. Right? The more brittle a component is, the more likely a small crack is to quickly form into a big crack. So you go to those higher frequencies to find those smaller flaws before they get to a critical size that can cause a failure, a catastrophic failure. So when you're selecting that frequency, it's a compromise between depth of penetration and sensitivity. Again, high frequency, high sensitivity, low depth of penetration, low frequency, relatively lower sensitivity, but higher depth of penetration. And then also balancing that conductivity and resistivity that we saw in the previous tables. And then the magnetic permeability that we saw in the previous tables. So we have to know, are we going to reach our expected flaw, but we don't want to reach beyond the expected flaw or beyond the opposite side of the part. Because if we're doing that, we're reducing our sensitivity with no gain. Right? If our depth of penetration is further than the thickness of the part, you're creating this real strong magnetic field in the surface that's going to obscure smaller cracks. And you're not, if my part is only the width of my finger and my depth of penetration is down here, I'm wasting all this, there's no reason to try to find cracks outside the part. So it's a balance of that. And as I mentioned earlier, you can have multi-frequency specialized testing where you can get a increased resolution over various depths rather than a single frequency. It does a low frequency pulse, then a high frequency pulse, then a low frequency pulse, then a high frequency pulse in order to get, it looks at the surface, looks deeper in the part, looks at the surface, looks at deeper, looks at the surface, looks at the backside, looks at the surface, looks at the backside. And when I say it's doing that very, very quickly. Fast enough that you can take your probe and as you move it around on your part, you're not going to know when it's doing top, it's doing it several times a second.